Welcome to our brief tutorial on exponential functions and their graphs. It's just to summarize the concept. So I want to first of all define what an exponential function is, then look at the graph and some of the features, and then finally we're going to look at an application or two. So first of all, what is an exponential function? We're used to seeing x being raised to a power when we look at polynomial functions. However, what defines an exponential function is that our independent variable, which we usually will use an x for, is in the exponent. So we have this parent function a to the x, f of x equals a to the x. And there is a stipulation here for a. A has to be a positive number, but it's not allowed to equal 1. Okay, so a can be anything greater than 0 except for 1. And we'll see why later on. Okay. So what's our domain? Our domain, if you think about this, the domain, if you recall, is what x is allowed to be. And if you have a value a and you're raising it to a power, you can raise it to any power you want as long as that power is a real number. So our domain in this case is that x is an element of the real numbers. Or you could use interval notation to say that x is somewhere between negative infinity and positive infinity, which of course includes all real numbers. The range, on the other hand, we have to think about a little bit. Okay? If we raise a to some power, the range is what the value of our function will equal. So if we're raising a to a power, let's think about some different possibilities. First of all, if we raise a to the 0 power, that's going to be 1, because anything to the 0 power is 1 except 0 to the 0. We already said a can't be 0. Secondly, if a is a positive number, then this is actually going to be getting bigger. Okay, our number, the value of our function is going to get really, really big, but it's going to be positive. On the other hand, if x is negative, if you recall, a negative in the exponent simply says to take the reciprocal of the value. So our number will get smaller, but it'll still be positive. It'll be smaller in magnitude. For instance, if x is negative 1, it will be 1 over a to the first. And if x is negative 2, it would be 1 over a squared. So we have here, it's decreasing, but it will still remain positive. And that's why our range is that x has to be greater than 0. Or I'm sorry, f of x has to be greater than 0. Or the range goes from 0 to infinity as an interval, if we use interval notation. So now we can look at the range of our function. because the value of our function will be getting smaller and smaller in magnitude, but it will still be greater than, it'll still be, so you see, because our function will be getting smaller and smaller in magnitude while still remaining positive, we would say that our range is that the value of the function will always have to be greater than 0. No matter what we plug in for x, it'll never end up equaling 0, and it'll never be negative. Okay, and you see here also, if you want to use interval notation, you can use the interval from 0 to positive infinity. So let's think a little bit more about what a can be. All right, we already said a has to be a positive number, but not equal to 1. So it eliminates 0 and everything in the negatives. However, there are two possibilities here. We could have a situation where we have what's known as exponential growth, okay, and that's where our function will be going like this. It'll be going up as we go to the right. For exponential growth, we can see that a would have to be greater than 1. Okay. And we'll see an example of that in a moment. For exponential decay, this is when we have a function that's actually starting high but then getting smaller as x increases. And for that to happen, a has to be a fraction between 0 and 1. Now, if you recall the connection that we've made between, if you recall what we learned earlier in the year about geometric sequences, you'll notice, remember, geometric sequences had that common ratio to the n power. Well, that's all this is. This is an exponential function. It's the same as a geometric sequence, except instead of us just being allowed to have integers, we can actually have all real numbers for x. Now, for a, if you recall, for our geometric sequences, we said that the sequence would keep getting larger and larger and larger as long as a was greater than 1. And that's why we were not able to find the sum of the infinite geometric sequence. However, we saw before that if a, we saw before that if r was a fraction between 0 and 1, our terms of the sequence got smaller and smaller and smaller, and they approached 0. And the reason why that's significant is because then we were able to find the sum of the infinite geometric sequence, because the entire sequence converged to 0. So here we see that connection. Now, let's look at the graph. I'm going to use an example so we can actually graph it of a to the x, which is 2 to the x, and we'll look at a couple of points specifically. I already mentioned that anything to the 0 power is 1. So if we plug in 0 for x, we have 2 to the 0 power, which is 1. And you'll see this function right here crosses right at the point 0, 1. Now, over here we have some general properties of the graph of a to the x. We already saw the domain and the range. The interesting thing is that the y-intercept, unless our function has been translated up or down, our y-intercept will always be the point 0, 1. Now, if we look at these other points, if we plug in 1, 2 to the first is 2, 2 to the second is 4. All right, and you can see here 2 to the first, we're at 2, and 2 to the second, we're up here at 4. Okay, and then 2 to the third would be 8 if we kept going. But as we go to the left, if x is negative 1, we have 2 to the negative 1 power, which means we're going to put 1 over 2, which gives us a half, 1/2. So here you can see we're at negative 1, 1/2. And then when we plug in negative 2, we have 1 over 2 squared, which would be 1/4. Okay, and you can see here at -2, we're at 1/4. Now you can see here, because A is bigger than 1, notice it's increasing as we go from left to right. Okay? If this was a 1/2 to the x instead of a 2 to the x, we would see this function going like this. So let's look at a quick application here. One of the common applications here is looking at exponential growth and decay that we mentioned earlier. But I want to look more closely at the value of A. You'll notice I've written it a little bit differently, and I also included another value in front of A, which is P. Alright, now I'm using a little bit of different notation. A of T is the amount of something we have after a certain time T. And of course T is our time. P is our starting amount. In other words, it doesn't have to be the start of something's existence. It just has to be the start of the time that we are looking at it. So we can start that at any moment. So basically just think of when is your T equal to 0? And that's your starting amount. And then finally, R is your rate of growth or decay. Now, if it's growth, R will be positive. If it's a decay, then we're going to lose a certain percent every unit of time, so R would be negative. That's what makes the A be a fraction between 0 and 1. And then a little note here that you need to make sure of. Make sure that your rate has the same unit of time as the time does. Make sure that the rate is a percent growth in 1 unit of time for this model. So if you're dealing with years, make sure your rate is in years. Or if you're given a rate in months and the time is in years, you can convert your years' time into months and rework your model. You just have to be careful about that. Let's do a real simple example here though to see how this works. Let's suppose a tree is 10 feet tall and grows in height by 2% each year. How tall will it be in 20 years? Well, if we start with our basic model, we need to identify our variables. The time frame we're looking at is the time of 20 years. P, the starting amount, in this case the starting height, is 10 feet tall. Now, obviously, the tree was shorter at one point, but we're starting the time today. So 10 feet tall would be P. And then the rate is 2%. So we would plug it in as a decimal of 0.02. So we substitute those values into our model. Starting amount times 1 plus the rate of change to the t power. We simplify by adding inside the parentheses, and then follow our normal operations to simplify, and we get 14.859 feet, which is approximately 14 feet 10.3 inches. So that's just a simple example of how this can be used. Let's look at one other example with a decay problem. This is just a problem from our textbook, and it says in early 2006 a new Jeep Wrangler Sport Edition had a manufacturer's suggested retail price of $23,970. After T years, the Jeep's value is given by value at time T equals 23,970 times 3/4 to the T power. Now notice where our model comes in. The starting amount, the starting price, is that value in front of the parentheses. This is already simplified, 1 plus R. Well, since it's decreasing in value as it gets older, R is negative, and to get a 3/4, we of course have to be losing 25% of its value each year. So here's, if we were setting up the model ourselves, that's how it would look. So first of all, let's look real quickly at a graph of this model. So if we graph this on our calculators here, we would see a model that looks like this. Notice here's our starting amount. In this case, the y-intercept is at 23,970, and then it's losing its value. Notice it loses value very quickly. After 3 years, it's only about a third of its original cost. And as it goes down here, you'll notice I plugged in 10 for X. After 10 years, this vehicle is only worth about $1,350. So it decreased very quickly. Now secondly, we can use this graphing calculator also to create a table of values. Let's take a look at the actual values rather than just a graph. You can see here, again on our calculators, notice here's our original price, and then notice in the first year it loses $6,000 of value, then another $4,500 in value. It decreases rather quickly, and it starts to level off as it gets older and older. It's until, between the 9th and 10th year, it's only losing about $450 in value. But one thing to take note of here, Part C, according to the model, when will the Jeep have no value? Well, think about the range of this function. The range of an exponential function, unless it's been transformed up or down, is that the value has to be greater than 0. So the fact of the matter is, the Jeep will never have no value. If you think about this practically, no matter how old a car is, it's still made of metal. You could still take it to a junkyard and scrap it for the metal, and they could recycle it, and you could get something out of it, even if it were 100 years old. So there's never a point at which it will have no value because of that horizontal asymptote there at 0. So this has just been a quick summary of our exponential functions, the graphs of them, and hopefully this will help tie everything together and help us to understand these functions a little bit better.